So I want you to imagine sitting across a chessboard from a reigning grandmaster.
Okay, I'm picturing it.
Right. And they open the game with this brilliant defense you've never seen it before. They are completely controlling the board.
Just totally dismantling you.
Exactly. They execute this seemingly impossible, like 12-move combination that leaves you absolutely speechless.
Wow.
And then, for their 13th move, they pick up a rook, and they just try to move it diagonally across the board.
Wait, diagonally?
Yeah. Completely oblivious to the basic rules of the piece.
Oh, man.
That jarring, almost vertigo-inducing paradox, utter transcendent brilliance combined with this sudden fundamental structural stupidity that is exactly the feeling we are all experiencing with modern artificial intelligence right now.
It really is. It's the perfect way to describe it.
Right. I mean, you can open a prompt window and have an incredibly sophisticated conversation.
Yeah.
You can ask a language model to synthesize the geopolitical causes of a historical war or explain quantum entanglement using the vocabulary of a 19th century poet.
And it does it.
It does it with this astonishing, seamless fluency. It feels like you are interfacing with this brilliant mind.
Yeah.
But then right in the middle of this high-level intellectual exchange, the system will just stumble on a logical relationship so basic, so structurally simple, that it completely shatters the illusion.
It's wild.
You're left sitting at your desk wondering how a system that possesses so much apparent knowledge can fail so fundamentally at, basic wiring.
Exactly.
So today, we are going to unpack the mechanics behind that exact paradox. Our insights for this deep dive come from Rooted Layers AI insights grounded on research. We'll be referring to their synthesis naturally as the post, as we sort of, think out loud today.
Yeah. And it is the perfect puzzle for us to pull apart, because that disconnect you just described between surface fluency and structural failure, it isn't just a quirky bug. It is arguably the single most important roadblock in the evolution of artificial intelligence right now.
Right.
Our mission today is to really move beyond that feeling of surprise and actually map the physical mechanics of this phenomenon. The post introduces a foundational mental model to explain this, which it calls the binding gap.
The binding gap.
Okay. And we are going on a pretty extensive microscopic journey today to understand it. We'll start by defining the bizarre behavioral quirks this gap produces. Then we are going to do something really fascinating.
I love fascinating. What are we doing?
We are going to look at the literal physical mathematics inside these neural networks to prove that this gap exists mechanically.
Oh, wow. Okay, lifting the hood.
Exactly. And we'll follow that up by looking at what happens when researchers stress test these models with complex real-world scientific data where, these failures stop being funny and start being highly consequential.
Yeah, where the stakes actually matter.
Exactly. Finally, we will discuss how uncovering this binding gap completely rewrites the agenda for the future of AI engineering. A useful way to think about this conversation is that we are shifting from treating AI as a magical, unpredictable black box to treating it as a mechanical engine with very specific, identifiable gears.
And we are going to look closely at the exact gear that keeps slipping.
You got it.
I love that approach. So we have our researcher hats on today. We're looking for the underlying patterns, and we're trying to map the exact borders of this problem rather than just marveling at the outputs.
Right. Let's get into the mechanics.
Let's jump right into the deep end with a concept that the post uses as its foundational anchor. This stems from a 2025 paper by researchers Boshi Wang and Huan Sun. They explore a phenomenon known as the reversal curse.
The reversal curse. It's such a great name.
It really is.
Yeah.
And the post gives this deceptively simple example of it in action. So imagine you open a fresh session with a language model, and you teach it a brand new, isolated fact. You type in, Tom Smith's wife is Mary Stone.
Pretty straightforward.
Right. Simple enough. The model absorbs this context. It confirms it. But then, immediately after, you ask the model, who is Mary Stone's husband?
And what happens?
The model's performance just falls off a cliff.
Oh, wow.
Yeah. It hesitates, or it hallucinates a totally different name, or it outright says it doesn't have enough information to answer.
See, when you first observe that behavior, it feels almost impossible.
Totally impossible.
Because logically, nothing new has been added to the world state. The exact same pair of individual entities is in play. The exact same marital relation exists between them. But Wang and Sun treat this reversal curse as a massive red flag.
How so?
Well, they argue that this isn't just a funny oddity you find on a standardized benchmark test. It actually exposes a foundational design flaw in the transformer architecture.
which is the underlying structure of basically all modern large language models. Right.
Exactly. Their core thesis is that these models are incredibly good at retaining the individual ingredients of a fact. Like, they know Tom, they know Mary, they know the concept of marriage.
Right.
But they fail completely at keeping the relation between those ingredients in a format that can survive a change in perspective or role assignment.
Okay, I really want to try and visualize what is actually happening inside the model when it fails at this.
Huh.
Because from a human perspective, relationships are almost always inherently bidirectional.
Right, yeah.
If I know that I'm your friend,
Mm.
I automatically know that you are my friend. If A equals B, B equals A,
Hmm.
my brain doesn't have to, store those as two completely separate, isolated files.
No, it's just one connected concept for us.
Right. But for the AI, the names Tom and Mary are still hovering there in its active memory. The semantic concept of a spouse is highly familiar to its training.
Yeah, the ingredients are there.
So what gives way, according to the post, is the attachment itself, the literal wiring that tells the system exactly which entity belongs in which slot in that specific relationship.
The wiring just snaps.
Uh-huh.
And Wang and Son's research points to two very specific internal pressures that cause that fragility. The first mechanism they identify is what they call inconsistency.
Inconsistency. Okay, what does that mean in this context?
Well, to understand this, we have to remember that language models don't read words like we do. They translate words into high-dimensional mathematical representations or vectors.
Right, a bunch of numbers.
Exactly. And what Wang and Son found is that a model literally represents an entity differently in its internal mathematical space, depending on the syntactic role that entity is currently occupying.
Wait, really?
Yeah. Tom functioning as a husband has a genuinely different mathematical signature than Tom functioning as the subject of a sentence. The math morphs based on the grammar.
Oh, wow. So because the word Tom is doing a different job in the second sentence, the AI's internal mathematical shape for Tom changes so much that it just, loses track of the connection to Mary.
That is a big piece of it, yes. But it is compounded by the second pressure they identified, which is entanglement.
Entanglement, like quantum entanglement.
Kind of, but in a semantic space. When a model learns, it isn't filing facts into neat, isolated folders. It is absorbing massive, continuous streams of data, and nearby concepts in its vast mathematical space start to pull on each other.
Ah, I see.
They interfere with one another, the representations get tangled up, so you have these inconsistent, shifting shapes for the entities combined with a highly entangled mathematical space.
So when you ask the model to reverse the relation and change the roles,
The specific fragile attachment holding Tom and Mary together simply cannot survive the transformation. It breaks.
okay, a useful way to think about this is like having all the ingredients for a highly complex recipe sitting out on your kitchen counter. You've got the flour, the eggs, the sugar, the baking powder.
All right, you're ready to bake.
You have absolutely everything you need. But you have completely misplaced the instructions that tell you which ingredient goes into which bowl and at what temperature.
Yes.
You know you need flour and eggs, but instead of baking a cake, you end up with scrambled eggs covered in raw flour.
Which is disgusting.
It's terrible. But the ingredients are in the room. They are fully available to you. But the delivery is disastrous because the instructions, the wiring, the attachment are missing.
That's a perfect analogy.
And what the post points out, which I find really deeply fascinating, is that because the ingredients are still in the room, the model doesn't just output total gibberish.
Right. It doesn't say, Mary Stone's husband is a toaster.
Exactly. It stays in the right neighborhood, which is what makes this failure mode so insidious.
Yeah, the outputs of a model suffering from this specific type of failure are rarely absurd. The Post uses a great phrase for this. The outputs are annoyingly adjacent to truth.
Annoyingly adjacent to truth. I love that.
The model keeps the overall scene intact, but it drops the internal wiring. If you ask it about a research paper, it remembers that we are talking about biology. It remembers the core topic, but it completely misplaces the specific citation.
Or if you ask it about a physics equation, it keeps the names of the variables, but it assigns the numerical value to the wrong pair.
Exactly. It provides the user with this incredibly convincing illusion that it knows exactly what it's talking about, but the specific granular answer it provides is structurally compromised.
You know, this fits a broader pattern we're seeing across the entire AI ecosystem right now. We have this crude catch-all umbrella term we use whenever an AI gets something wrong. We say the AI hallucinated.
Oh, I hate that term sometimes.
Right. Because if we just call everything a hallucination, we are lumping together fundamentally different mechanical failures. It's like a doctor diagnosing every single ailment as a fever.
It doesn't help you cure the patient at all.
Exactly. And that logically moves us to the next major argument in the post.
Yeah.
If we want to understand this, we need to draw strict, uncompromising borders around this phenomenon. We need a highly precise vocabulary.
We do.
And the post proposes the specific term for this exact failure, the binding gap.
Yeah, and the author of the post is incredibly meticulous about this definition. Establishing a new term in a field moving this fast only works if the borders of that term stay incredibly clear.
So how do they define the borders?
Well, they dedicate a significant portion of the synthesis to defining what the binding gap is not. It is essentially a process of diagnostic elimination.
Okay, process of elimination. Walk me through it.
First, they point out that a binding gap is not a retrieval miss. There is research cited here by Boulos et al. From 2026, which examines systems designed to search external databases or the internet for retrieval augmented generation.
Right, RAG.
If the system executes a search, fails to find the correct document, and therefore never brings the needed evidence into its working memory, that is a retrieval miss. The information was simply never on the table to begin with.
Because, going back to our recipe analogy, for it to be a binding gap, the flour and the eggs have to actually be in the kitchen. If you never went to the grocery store to buy the eggs, you can't blame a binding failure.
Exactly that. The ingredients must be present. Second, the post draws a boundary against what it calls a downstream context utilization failure, referencing a 2026 paper by Pandy.
Okay, what's that?
Imagine the model does retrieve the right document. The exact answer is sitting right there in its context window, plain as day. But for whatever reason, perhaps the user's prompt was overly complex or the document was 50 pages long and overwhelmed the attention mechanism. The model just ignores that specific paragraph entirely and goes off on a tangent.
So it saw it, but ignored it.
Right.
Huh.
That is a failure to utilize provided context. The system ignored the ingredient entirely rather than trying to use it and wiring it incorrectly.
Got it. What's next?
Third, it is not a decomposition failure. This happens when you give a model a complex, multi-step logic or math problem, and it just breaks a problem apart completely wrong from step one. It heads down the wrong logical path entirely, solving the wrong subproblems.
Okay, I track that. And finally, the post is very clear that the binding gap is not what we would call a generic hallucination.
Right.
The catch-all. A generic hallucination is when the model just completely untethers from reality and from any factual support provided in the prompt. It starts fabricating content from scratch, making up fake legal precedents, inventing historical figures out of whole cloth, or creating fictional academic papers.
There's no preserved semantic material from the prompt being miswired there.
Exactly. It's just the model's text generation engine running hot and producing pure fiction.
So if we strip all of those other distinct mechanical failures away, what are we left with?
We are left with the post's 3 marks of a true, verifiable binding gap failure. These are the diagnostic criteria that engineers need to look for.
Okay, let's hear the 3 marks. Mark number 1. The relevant pieces, the semantic materials, the names, the numbers, are present enough in the output that the model's answer feels uncomfortably close to the truth.
Right, the scrambled eggs with raw flour.
Exactly. Mark number 2. The error becomes visible exactly at the moment when a specific role, a specific source attribution, or a specific numeric attachment really matters. It's the inversion, the reassignment, or the precise pairing that breaks the system.
And mark 3.
Mark number 3. The failure cannot be better explained by one of those other categories we just eliminated, like a missing database retrieval or solving the wrong mathematical subtask.
So it's a very narrow, specific diagnosis.
Yes. When you have all 3 of those marks present simultaneously, you are looking at the binding gap. You are looking at a system that possesses the pieces but fundamentally lost the wiring.
Okay, here's where it gets incredibly interesting. But I feel the need to push back just a little bit, or at least play devil's advocate for you, the listener, who might be wondering about the practicality of this.
Sure, lay it on me.
I can hear someone thinking, okay, this taxonomy is very intellectually stimulating. I understand the difference between a retrieval miss and a binding gap. But are we just splitting hairs here for the sake of writing academic papers?
That's a fair question.
Right. Like, why does it matter so much if we insist on calling it a binding gap versus just saying the AI hallucinated a connection or got confused by the prompt? Does this level of linguistic precision actually change anything for the person trying to build or use these models?
It is a vital question because taxonomy without application is just, well, trivia. But the precision here is what actually leads to engineering solutions.
How so?
Let's use a mechanical analogy. If you have a complex piece of heavy machinery on a factory floor and it stops working, and you misdiagnose a broken electrical wire as a dead battery, you are going to spend all day swapping in fresh batteries, and you will never fix the machine.
Right. You're treating the wrong disease.
Exactly. The umbrella term hallucination is the equivalent of just saying the machine is broken. It completely flattens the landscape of AI failures. If an AI engineer thinks a model is hallucinating a factual connection because it simply lacks knowledge, their instinct will be to fix it by feeding the model more data.
They will train it on more books, expand its database, give it more parameters.
Yep. But if the problem is actually a binding gap, feeding the model more data won't help at all.
Because more data doesn't fix the wire. In fact, if we go back to what Wang and Sun said about entanglement, dumping more data into the model might actually increase the mathematical entanglement and make the binding gap even worse.
It absolutely could. By isolating this specific family of high-consequence failures, failures where the structural attachment matters more than the topical familiarity, researchers can stop throwing raw data at the problem and start designing highly targeted architectural interventions. Narrow, defensible terms allow us to isolate the exact mechanical flaw.
That broken wire analogy actually perfectly sets up the entire next phase of our exploration. Because if we are going to sit here and confidently claim that there's a broken wire inside the AI, we have a burden of proof.
We do.
We have to prove that there are actual wires in there to begin with. We have to ask the hard question. Is this idea of binding just an external psychological metaphor we are imposing on the model's text output to make ourselves feel better? Or is there actual physical mathematical machinery inside the artificial neural network that handles and drops these bindings?
And that is exactly where the post explicitly transitions from behavioral observation to mechanistic evidence. We are lifting the hood on the engine.
I am so ready for this.
Good, because this is where the research crosses over from computer science into something that feels almost like digital neuroscience. The post acknowledges that if binding were just an external label we slap on bad paragraphs, it would be a weak, untestable theory. But the mechanistic interpretability literature has moved far beyond that. We now have concrete proof that binding is a task solved internally with dedicated mathematical structures.
Dedicated structures. Okay, lay it out.
The post highlights a pivotal 2023 paper by researchers Feng and Steinhardt that looks specifically at in-context entity binding. What they discovered fundamentally changes how we view these models.
What did they find?
They found that language models don't just rely on a vague, amorphous cloud of general semantic association to keep things together. When they need to link two things, they actually generate and attach specific internal mathematical structures, which Feng and Steinhardt call binding ID vectors, to entities and their attributes.
Okay, I really want to slow down and unpack what a binding ID vector is, because we're talking about visualizing the internal invisible brain activity of the AI.
Right.
A vector, in the context of machine learning, is essentially a very long list of numbers. You can think of it as a coordinate or a direction and a magnitude, pointing somewhere in an unimaginably high-dimensional mathematical space.
Exactly. It's how the AI represents any concept.
And what I understand Feng and Steinhardt to be saying is that when the AI reads a simple sentence like the red apple is on the table, it doesn't just light up the apple concept and the red concept in a general glowing soup of activation.
No, it's way more specific than that.
It literally generates a specific newly minted ID tag vector, and it physically integrates that tag into the mathematical representations of both apple and red across its internal processing layers to lock them together.
That is a phenomenal way to visualize it. It is a discrete, internally generated mechanism for attachment. It is a temporary lock and key.
Wow.
And the reason we know this isn't just a theory is because researchers can perform what are called causal interventions.
Causal interventions, what does that mean?
They don't just observe the network, they actively mess with it. They can run a prompt through the active neural network, pause the computation midstream, locate these specific binding ID vectors within the layers, and surgically alter the numbers.
They literally reach into the math.
Yes. They reach into the high-dimensional math and do vector subtraction to unbind the red from the apple. And when they let the model finish computing, the output changes accordingly.
That is wild.
But the research gets even more hyperspecific than that. The post brings in a subsequent 2024 paper by Dai, Heinzerling, and Inoue. They pushed this mechanistic search even further. They didn't just find these general ID tags. They identified a very specific location, a low-rank ordering subspace.
Okay, low-rank ordering subspace. That sounds incredibly intimidating.
It's a mouthful.
It sounds like something an engineer would yell about in a science fiction movie right before the warp drive explodes. Let's translate that into plain English. What is a subspace and how does it order things?
Think of the model's total internal representation space as a massive multi-dimensional volume. We humans live in 3 dimensions, but these models operate in spaces with tens of thousands of dimensions.
Hard to picture, but okay.
A subspace is just a specific, smaller section or geometric plane cut through that massive volume. What Dye, Heinzerling, and Inouye discovered is that there is a highly specific geometric area inside the model whose entire job, its only function, is to steer which attribute gets bound to which entity based on the order they appeared in the text.
Wait, so it's a dedicated switchboard.
It functions exactly as the physical switchboard. The post gives a brilliant example of a causal intervention targeting this specific area. Imagine you give the model a prompt describing a box that contains coffee and a bag that contains a stone.
Okay, box has coffee, bag has a stone.
The researchers can pause the model, go into the specific ordering subspace, and mathematically patch or invert the direction of the vectors in that exact location.
It's flipping the numbers.
Right. They don't change the words box, bag, coffee, or stone. They just flip the switchboard.
Oh.
And suddenly the model will confidently output that the box contains the stone and the bag contains the coffee.
That is staggering. It means we aren't just looking at the output of a mysterious black box anymore, where we throw a bunch of words in, cross our fingers, and pray that good words come out the other side.
No, we are mapping the circuitry.
We have actually found the tiny internal switchboard operator inside the neural network. We can watch them physically unplugging the stone cable from the bag jack and plugging it into the box jack. We are mapping the anatomy of artificial thought.
The implications of this for how we build, test, and debug AI in the future are profound. Historically, when a language model made a factual mistake, engineers had a very blunt toolkit.
Just retraining it, right?
Yeah, they would adjust massive system-wide learning parameters, or they would try to filter the training data and just hope the model learned the pattern better the next time. But if we can isolate the exact mathematical vector and the exact subspace that binds a specific attribute to a specific object, the future of AI debugging looks entirely different.
How so?
It looks much more like neurosurgery. If a medical AI hallucinates a dangerous interaction between 2 drugs, we might not need to retrain a trillion-parameter model from scratch. We might be able to go in and adjust the specific subspace where that binding failed to take hold. We are moving from behavioral psychology to cellular biology in how we treat these systems.
It fundamentally changes the paradigm of what it means to improve an AI. But, and I think this is a necessary transition point, it's one thing to bind a single simple attribute to a single simple object.
A stone in a bag.
Right, or the color red to an apple. Those are very isolated, almost toy-like laboratory examples.
Yeah.
How does this internal switchboard handle the messy, ambiguous, incredibly complex flow of natural human language?
Oh, it struggles.
Because when we speak or write, we don't just list entity-attribute pairs. We tell complex stories. We describe cascading events with multiple actors.
This is where the challenge scales up exponentially, and it brings us to the bridge from simple entity binding to what linguists call thematic role assignment.
Thematic role assignment.
Yes. Thematic role assignment is the deep machinery of who did what to whom. It's the event structure, the causal logic of a sentence. The post introduces a crucial 2025 paper by Denning, Guo, Snefjella, and Blank that investigates how language models handle this exact bridge.
Okay, what do they do?
Well, in natural language, you can have 2 sentences that share the exact same vocabulary, the exact same entities, but have completely reversed event structures. The classic linguistic example is the dog bit the man versus the man bit the dog.
Right.
The entities man, dog are identical, the action biting is identical, but the roles, the agent who initiates the action and the patient who receives the action, are completely swapped.
And for a human being listening to those sentences, that role assignment is the single most important part of the communication.
Absolutely.
It dictates the entire meaning, the entire mental image, and the entire consequence of the event. If you tell me the man bit the dog, my brain immediately flags that as a highly unusual, specific, newsworthy event, entirely because of how the roles are assigned. The structure dominates the meaning.
And that is exactly where human cognition and AI computation diverge wildly. Humans integrate thematic roles incredibly strongly into our overall understanding of a situation. But what Denning and their colleagues found through their experiments is that while large language models can extract agent and patient information,
Wait, they can extract it.
yes, they do possess internal mathematical mechanisms that recognize who is the subject and who is the object. But that role information influences the model's overall representation of the sentence much more weakly than it does in humans.
So they see it, but they don't care as much.
Exactly. The model captures the roles, yes, but the role structure does not dominate the model's broader thoughts or semantic associations about the sentence. The structure is secondary to the vocabulary.
Okay, the post then layers in another piece of evidence, a 2025 paper by Al-Jafari, Carvalho, and Freitas, which looks at the specific circuitry inside the models handling these roles.
Yes, and they found that there are indeed compact, causally localized circuits inside the models dedicated to processing semantic roles. So the machinery is definitively there, it's not missing.
But when you put the Denning paper and the Al-Jafari paper together, the post advocates for what it calls a precise middle position. And understanding this precise middle position is absolutely crucial to understanding the limits of modern AI.
It is the key to the whole thing.
The position is this. Role binding is real inside the system. The circuits exist. But it is so weakly integrated into the broader network, or so fundamentally fragile, that the model can maintain an incredibly high level of surface fluency while having completely unstable structural attachments underneath.
It exposes the central paradox of the current generative AI boom. You can have a model write a beautifully flowing, grammatically pristine, highly articulate 4-paragraph essay describing a complex historical battle.
Right, it sounds like a historian wrote it.
Exactly. While simultaneously, on a deep structural level, it is fundamentally confusing which army actually initiated the flank and which army retreated. The surface of the text looks pristine, but the structural load-bearing pillars underneath are made of sand.
I have to pause here because this creates a huge cognitive dissonance for me, and I'm sure for anyone listening who uses these tools daily.
Oh, I'm sure.
If the system's grasp on who did what to whom was so inherently fragile, and if it's so weakly integrated compared to a human brain, how are these models passing the bar exam? How are they writing coherent college-level essays that fool professors? How is the illusion of deep competence so incredibly convincing if the underlying binding is constantly on the verge of snapping?
It is a great question, and it forces us to look at how these models actually generate text. These models are trained on the statistical patterns of trillions of words scraped from the internet. In standard, everyday conversational text, or even in broad, open-ended essay writing, broad semantic association is often enough to fake structural comprehension.
Fake it. How do you fake that?
Well, if you ask an AI to write an essay about the causes of the French Revolution, the general statistical cloud of concepts, famine, taxation, Marie Antoinette, the guillotine, the Bastille, is so incredibly dense and so highly correlated in the training data that the model can string them together fluently without needing perfectly rigid, complex causal bindings at every single step.
Ah, I see.
The sheer statistical momentum of the language itself carries the model through the paragraph. It is surfing on the statistical wave of human language.
Okay, that makes sense. Because human language is so full of predictable patterns, cliches, and redundancies, the model can sort of surf on top of those waves without ever having to dive down and rigidly bind the underlying logic. It just knows that words about the French Revolution generally sound like this.
Exactly.
But that makes me wonder about us. Why do human brains integrate thematic roles so much more strongly? Why does who did what to whom dominate our representations, while it's just a weak, easily dropped signal for a multi-billion parameter transformer?
It almost certainly comes down to our physical embodiment. Humans are physical creatures existing in a physical world governed by strict, unforgiving laws of cause and effect.
Right, gravity, momentum, all of it.
From the moment a human infant is born, they learn about agents and patience by interacting with physics. A baby pushes a block, and the block moves. The baby is the agent. The block is the patient. If the baby doesn't push, the block doesn't move.
Action and reaction.
Exactly. Our entire cognitive architecture, our entire brain is built from the ground up to track causal relationships because our physical survival depends on it.
And the AI?
A language model has no body, no physical world, no sensory input, and no inherent concept of cause and effect. It is trained purely on predicting the next token in a string of text. It learns the shapes of words, not the physics of the world.
Wow.
So it naturally builds an internal architecture where statistical co-occurrence is the dominant driving force and rigorous structural binding is a secondary fragile byproduct.
That is a profound distinction. We learn from interacting with physics. They learn from mapping syntax. So if broad semantic association is enough to fake it in an essay or a casual chat or even a poetry generation prompt, what happens when we remove the safety net of those statistical patterns?
Things get messy.
What happens when we raise the stakes, strip away the narrative fluff, and force the model into an environment where it has to handle dense, mathematically rigid relationships where broad association is completely useless?
That is exactly where the illusion shatters, and that is where the post takes us next to prove its point. To truly see the catastrophic nature of the binding gap in action, we need an ultimate stress test.
An ultimate stress test. What do they do?
The post points to a 2026 paper by researchers Z10 and Jennifer D'Souza as the strongest, most rigorous version of this test. They took these advanced language models out of the comfortable realm of writing essays and generating code snippets, and they put them to work on a grueling, highly unforgiving, real-world scientific task.
Which was?
Evidence extraction for meta-analysis.
Okay, I think we need to define what that setting actually looks like, because a meta-analysis is intense work. A meta-analysis is essentially a master study that combines the statistical results of multiple independent scientific studies to find an overall truth.
Right, it's the gold standard in science.
To do this, human researchers have to read dozens, sometimes hundreds, of incredibly dense scientific papers, and they have to extract highly specific structured data records from the prose. They have to read a 30-page PDF and turn it into a rigid database.
Exactly.
You need to find the specific variables being tested, the specific statistical methods being used to compare them, the specific roles of those variables, which one is dependent, which one is independent, and the exact numerical effect sizes. And they have to keep all of those data points perfectly, rigidly linked together.
And as Tan and D'Souza point out in their methodology, the difficulty here isn't just spotting isolated pieces of information. It's not a word search. Language models are actually quite good at spotting isolated entities. If you upload a scientific paper and ask a model a simple single property query like, what was the name of the dependent variable in experiment 2? Okay. It performs moderately well. It can find the token.
Okay.
The real difficulty, the absolute crux of the meta-analysis task, is preserving the relations that make those isolated data points analytically usable. You have to know which specific variable is paired with which specific role, under which specific statistical method, to produce which specific numerical effect size.
It is a massive, highly entangled web of rigid mathematical attachments.
It's a nightmare for a transformer.
Let's walk through a simulated example of how this breaks down, just to make it concrete. Imagine an AI is reading a paper studying the effects of a new beta blocker drug. The paper says, in cohort A, taking the beta blocker, heart rate decreased by 15 beats per minute using an ANOVA analysis. In cohort B, taking the placebo, heart rate remained stable, but reports of nausea increased by 20% based on a chi-square test.
Okay, dense paragraph.
Right. The AI reads that. It successfully identifies all the tokens. Cohort A, Cohort B, beta blocker, placebo, heart rate, nausea, 15 BPM, 20%, ANOVA, chi-square. It has the ingredients.
Yeah.
But what happens to the math when it tries to extract the full association?
The results of Tan and D'Souza's stress test show that this is exactly where the models degrade sharply. When asked to extract full association tuples, meaning the complete, perfectly linked set of data points across the entire document, their reliability drops to near zero.
Near zero. Wow.
And what makes this paper so critical for understanding the binding gap is that the researchers documented the specific patterns of how the models failed. They didn't just fail randomly, they failed in ways that scream binding gap.
What kind of failures?
For example, they found frequent role reversals, where the model successfully identified the independent and dependent variables, but swapped their positions in the final output.
Just swap them.
They found cross-analysis binding drift. In your example, the model might correctly extract the beta blocker heart rate data, but wrongly state that it was analyzed using the chi-square test from the other paragraph. The method drifted across the semantic space and attached to the wrong node.
Yikes. What else?
They also found what they call instance compression in dense result sections. This is when a paragraph lists 4 or 5 different data points back to back, and the model, unable to maintain 4 separate binding structures simultaneously, just mushes them together, blending variables from one study with numbers from another.
Just a blended mess.
And finally, they found massive numeric misattribution, which is simply assigning the right numbers to the wrong variables. It knows 20% is important, but it attaches it to the heart rate instead of the nausea.
This is the perfect, terrifying, real-world manifestation of the binding gap. Because, as the post emphasizes, this specific list of errors completely destroys the easy excuse that the model just didn't see the information or that the context window was too small.
The papers were in the context window.
Exactly. The models often correctly recognize the variable names. They correctly recognize the statistical methods. They successfully identify the exact numbers in the text. All the ingredients were in the room.
They were.
The collapse happened purely because the internal mathematical representation could not keep them securely attached to one another across the density of the scientific text and the changing scope of the sentences.
It fits a broader pattern we're seeing across enterprise AI deployment, and it highlights a critical, often ignored danger. AI fails exactly at the point where faithful, reliable use actually begins. In a scientific or research setting, a system that identifies the correct numerical effect size but binds it to the wrong variable pair hasn't just made a slight acceptable error. It has produced something worse than useless.
It has produced highly confident misinformation. The exact same goes for carrying a statistical method into the wrong comparison. A useful way to think about this is like an overwhelmed waiter at a very busy, very noisy restaurant. You have a table of 6 people, and they all fire off complex, highly specific orders in rapid succession. I'll have the steak, medium rare, no asparagus, substitute potatoes. I'll have the salmon sauce on the side, chicken, extra asparagus.
I'm stressed just listening to that.
Right. The waiter stands there, they listen intently, they nod, but they don't write anything down. They've heard the order perfectly. Their acoustic processing worked. They know that somewhere at table 4, a steak exists, a salmon exists, potatoes exist, and a side sauce exists. The ingredients are logged in their short-term memory.
Yep, the items are retrieved.
But under the immense pressure of the noisy environment, the entanglement of all those requests, they completely drop the internal wiring. They bring the salmon with no asparagus, the steak with sauce on the side, and they confidently hand the substituted potatoes to the person who ordered the chicken.
Exactly.
They kept the semantic neighborhood of the table's overall order perfectly intact, but the delivery is disastrous because the precise individual attachment failed.
That is an excellent analogy, and it scales up terrifyingly well to the real-world stakes we are talking about. Let's paint a vivid picture of what this means outside of a restaurant in a setting like healthcare.
Oh, healthcare.
Yeah.
This is where it gets scary.
Imagine a major hospital network deciding to deploy an advanced language model to rapidly summarize thousands of dense clinical trials to help busy oncologists make treatment decisions. The AI is fed a trial about a new experimental chemotherapy drug, let's call it Drug X, being compared to a standard placebo.
Okay, Drug X versus placebo.
The paper's dense results section notes that Drug X showed a remarkable 40% reduction in tumor size, while the placebo group experienced severe, unrelated side effects like internal bleeding. The AI processes this complex text. It successfully extracts the core entities. Drug X, placebo, 40% reduction, severe internal bleeding. It has the ingredients. But due to the binding gap, under the mathematical pressure of the dense medical jargon, the internal switchboard flips. It swaps the roles.
Oh, no.
It outputs a beautifully written, highly professional summary for the oncologist that says, the clinical trial showed that Drug X is associated with severe internal bleeding, while the placebo showed a 40% reduction in tumor size.
Wow. That is genuinely chilling, because the semantic neighborhood is perfectly flawlessly correct. If you just skim the summary, it sounds highly technical, highly plausible, and perfectly fluent. It doesn't sound like a hallucination. It sounds like a medical report.
It sounds completely legitimate.
But the internal wiring failure has literally inverted reality, making the output incredibly dangerous for a patient. And if a system can fail this disastrously while still sounding completely confident, and while outputting real source data points, it means we have a massive systemic blind spot in how we are judging these tools. We cannot trust our traditional, intuitive ways of judging whether an AI is correct or not. Fluency is not a proxy for structural accuracy.
That realization brings us to the disciplinary anchor of the post, and perhaps its most important philosophical argument, the trap of surface correctness. The post introduces a 2024 paper by Denitsa Sinova and her collaborators. Sinova's team investigated a very fundamental question. When a language model gives you a correct factual answer, how did it actually arrive there mechanically?
All right, how did it know?
And what they found completely shatters the comforting illusion that a right answer means the model understands the fact. They discovered that correct factual completions can arise from several entirely distinct internal mechanisms, and most of them have nothing to do with stable knowledge.
I really want to dive into this because this challenges everything we assume about interacting with AI. Sinova found 4 distinct paths a model can take to arrive at a correct answer. Let's walk through them.
Let's do it.
The first one is what we hope the model is doing every time, exact fact recall. The model is asked a question, it accesses a stable, securely bound representation of that fact in its internal geometry, and it outputs it. The wire is intact. But the other 3 mechanisms are where the illusion takes hold.
Yes. The second mechanism is heuristics recall. In this scenario, the model doesn't actually have a rigid binding for the specific fact requested, but it applies a general statistical rule of thumb that happens to lead to the correct answer in this specific edge case. It's taking a structural shortcut.
Like a lucky guess based on a rule.
Right. The third mechanism is simple guesswork. The model essentially flips a mathematically weighted coin based on limited context the text prediction engine fires, and it simply gets lucky.
Just rolling the dice.
Exactly. But the fourth mechanism is the most pervasive and the most deceptive. They call it generic language modeling pressure.
Generic language modeling pressure. Let's explain what that actually means mechanically, because it sounds like jargon, but it explains so much of the AI's behavior.
Let's hear it.
Imagine I ask a model, what is the capital of France? And it outputs the word Paris. As a human, I assume the model retrieved a securely bound, factual relationship between the concept of capital, the entity France, and the entity Paris.
Right.
But generic language modeling pressure means that even if the model has completely lost that specific, rigid relational binding, even if the wire is completely severed, the word Paris is just statistically so overwhelmingly common in the broad semantic cloud of words related to France, cities, and Europe that the text prediction engine just outputs Paris by default.
It's a statistical reflex, not a retrieved memory.
Exactly. It gets the right answer purely because Paris is a highly probable token in that semantic neighborhood, not because it successfully navigated a rigid logical relationship.
It is the ultimate parlor trick. And this is why the post emphatically declares that surface correctness is a weak witness. If an AI gives you the right answer to a question, it absolutely does not prove that the model preserved a stable, task-ready, reliable relation in its internal machinery. It might have just gotten lucky via heuristics or generic statistical pressure surfing.
And conversely, if it gives you a wrong answer, it doesn't mean all traces of the correct fact vanished from its training data. It might just mean the fragile binding snapped at the very last millisecond of computation. I find this deeply frustrating as someone who uses these tools because it completely upends how we think about evaluating AI competence. The post points out that the concept of the binding gap prevents us from telling what it calls a hidden knowledge story about AI.
We do love to tell ourselves that story.
We do. We like to anthropomorphize. We say the AI is like a brilliant but sleepy student who has read every book in the library, and if it gets a multiple choice question right, it means it knows the material. But Sinova's work and the reality of the binding gap forces us to look way beyond topical familiarity. It forces us to realize that knowing the ingredients and maintaining the wiring are 2 entirely different computational acts for these machines.
It raises massive systemic implications for the entire tech industry. Right now, there is an arms race to build the biggest, smartest AI. And the way companies prove their AI is better than the competitors is by running it through standardized benchmarks.
All right, the leaderboards.
Exactly. They ask it thousands of multiple choice questions, or they ask it to summarize Wikipedia articles, and if it scores 95% surface correctness, they put out a press release and declare victory. But if those standard benchmarks are predominantly measuring topical fluency and generic language modeling pressure, if they aren't aggressively testing the structural integrity of the internal bindings under stress, are we just building a massive trillion-dollar house of cards?
That's the billion-dollar question.
Are we deploying systems into medical, legal, and scientific fields that have a fundamentally brittle architecture hidden underneath a veneer of perfect grammar?
I have to express genuine frustration here, because this raises an incredibly difficult question for you, the end user. If even the correct answers might just be lucky guesses based on generic statistical reflexes, how can you ever trust what you are looking at?
It's hard to know.
If I use an AI to help me research a complex legal precedent, and it gives me a perfectly cited, highly detailed, beautifully structured answer, I have absolutely no way of knowing if that output was generated by stable, reliable internal circuit, or if it was just a fragile statistical house of cards that just happened to not collapse on this specific prompt. Are we fundamentally evaluating these tools the wrong way? Have we been grading them on their handwriting instead of their math?
The short, difficult answer is yes, we have been evaluating them the wrong way. We've been completely seduced by fluency. But the frustration you are expressing is actually the necessary catalyst for the final phase of the post's argument.
Okay, where does it go from here?
The realization that the binding gap exists, that it is a physical, mechanical failure, and that surface correctness is a statistical trap, shouldn't cause us to throw our hands up in despair and abandon AI. Instead, it gives the research and engineering community a highly concrete, highly specific roadmap to actually fix the technology. It fundamentally changes the agenda for the future.
Because if we finally know exactly how and why the wire is broken, we can start engineering better wires. The post outlines a two-pronged approach for this future agenda. Major changes in how we evaluate models, and major changes in the actual architectural design of the models themselves. Let's start with the evaluation side.
Let's hear it.
The post argues that we have to stop treating topical fluency, the ability to sound human and articulate, as a sufficient proxy for competence.
The era of testing billion-dollar models by having them write sonnets or open-ended essays needs to end, or at least be recognized as a superficial parlor trick. The new evaluation agenda must put intense, relentless adversarial pressure on exact role assignment, source attachment, and numeric grounding.
So we need harder tests.
We need benchmarks that are specifically designed to be binding heavy. We need tests that look exactly like Tan and D'Souza's meta-analysis extraction. Dense, rigid, deeply entangled webs of variables and numbers where any generic statistical guessing, any reliance on language modeling pressure will immediately lead to a catastrophic, measurable failure. We have to start testing the joints, not just admiring the paint job.
And once we are testing the joints properly and exposing the flaws, we can start implementing actual architectural interventions to reinforce them. The post highlights several potential solutions that engineers are currently exploring on the bleeding edge of AI research. One fascinating approach is called schema-aware intermediate records.
Oh, that's an interesting one.
This essentially means forcing the model to explicitly write out the structural logic of the data it is processing before it generates text.
What?
It's like forcing a math student to show their work. The model has to draw a literal mathematical map of the entities and their relations before it is allowed to generate its final output paragraph. It creates an explicit external scaffolding so the system doesn't have to rely entirely on its fragile, internal, high-dimensional vectors to keep things straight.
Another major intervention they discuss is provenance-aware training. This means changing the fundamental way the model learns from its training data in the first place. Instead of just absorbing a fact and letting it dissolve into a general, entangled soup of semantic knowledge, the architecture forces the model to maintain a rigid, permanent mathematical link between a fact and the specific document or the specific source that provided that fact. It anchors the knowledge.
It anchors it, I like that.
And perhaps most importantly, referencing back to the Wang and Sun paper we started with, they discuss the need for role-stable internal representations.
Right, addressing the inconsistency problem where the math changes based on the grammar.
Exactly. The goal is to design entirely new neural network architectures, perhaps moving beyond the standard transformer to architectures like JEPA or joint embedding predictive architectures, where the internal mathematical representation of the entity Tom doesn't radically morph and change shape just because he moves from being the subject of a sentence to being the object.
So the token stays the same.
If the mathematical representation is stable regardless of its syntactic role, the binding attaching him to Mary is much less likely to snap under the pressure of entanglement.
If we pull all of this together and connect it to the bigger picture, the author of the post distills all of this complex research down to one incredibly sharp, almost provocative wager. The post says this is a wager sharp enough to be proven wrong, which, as any scientist knows, is the hallmark of a truly great theory. The wager is this: if the binding gap is a real fundamental family of mechanical failures, then as we push models harder in the real world, binding heavy tasks will break much, much earlier than broad topical tasks.
Let's lay out the specific predictions of that wager, because they really serve as a roadmap for the next 5 years of AI research. The post predicts that role reversal will expose catastrophic weakness in models long before open-ended explanation does. It predicts that source attribution keeping, a fact tied to its citation, will fail long before generic text summarization fails.
Right.
It predicts that multi-field scientific extraction, like the meta-analysis we discussed, will completely collapse before simple entity spotting shows any degradation. And most importantly, for the engineers building the future, it wagers that the architectural interventions we just discussed, the schema records, the role-stable representations, will buy their first serious measurable performance gains on these dense, binding-heavy tasks long before they make the model any better at writing a generic, fluent essay.
So if I am understanding this wager correctly, the Post is essentially throwing down a gauntlet to the entire industry. It is daring the AI community, the companies spending billions on compute power, to stop testing their models on writing poetry or summarizing Wikipedia pages, and instead test them on keeping 50 distinct scientific variables tied to their exact origins, with their exact effect sizes and their exact statistical methods, without slipping once.
That's the real challenge.
That is the real frontier of artificial intelligence. If those asymmetries appear, if the models consistently fail at rigid binding while still excelling at statistical fluency, then the binding gap is real, and the entire industry needs to pivot its focus away from scale and toward structure. Progress, as the Post states, matters most not in making models sound more human, but in preserving the exact attachments that faithful, reliable use actually depends on.
And conversely, if those asymmetries do not appear, then the concept of the binding gap is too loose, and we are back to the drawing board. But given the overwhelming wealth of mechanistic evidence, from Wang and Son's reversal curse to Fang and Steinhardt's binding vectors to Dai's causal interventions in the switchboard subspace to Tan and D'Souza's meta-analysis collapse, the evidence strongly suggests this wager will hold true.
It seems highly probable.
The binding gap gives us a powerful, precise new lens. It forces us to stop asking the shallow question, what facts did the model memorize? And start asking the structural question, did it keep those facts attached in the exact logical form the task required?
This has been an absolutely incredible, eye-opening journey. We started with a simple, almost trivial puzzle, the reversal curse, where an AI knows Tom and Mary are married but forgets who Mary's husband is. And by pulling relentlessly on that single thread, we've unpacked the entire internal mathematical machinery of modern artificial intelligence.
We really went deep today.
We moved from behavioral quirks to finding the literal internal high-dimensional vectors where concepts are bound together, to seeing how terrifyingly fragile those bindings are compared to human cognition. We looked at the real-world consequences of this fragility in scientific research, where swapping a variable and a placebo can invert reality. And finally, we realized that our human obsession with surface correctness and fluency has blinded us to the structural weaknesses of these systems, requiring a completely new, rigorous agenda for how we evaluate and build the future of AI. The ultimate takeaway here is that true competence, whether in a silicon machine or a biological mind, isn't just about having the ingredients in the room. It's about keeping them accurately, rigorously connected under immense pressure.
It is a profound shift in perspective. And as we wrap up this deep dive, I want to leave you, the listener, with a final, lingering thought that builds on everything we've discussed today. We spent this entire time dissecting the mechanical failures of artificial intelligence, marveling at how a system can possess so much semantic knowledge, yet struggle so fundamentally with the binding gap, with keeping concepts cleanly separated and properly attached under the pressures of mathematical entanglement and inconsistency.
Yeah.
But as we map the anatomy of artificial thought, it makes you wonder deeply about human cognition. Think about the architecture of your own mind. Have you ever vividly remembered a brilliant, insightful quote, but confidently attributed it to the wrong person?
All the time.
Have you ever recalled a childhood memory perfectly, seeing the scene in vivid detail, only to realize years later that you swapped the roles and it was actually your sibling who took the action, not you?
Oh, absolutely.
When we suffer from our own biological versions of entanglement and inconsistency, when our own memories drift and misattribute under the pressure of time, emotion, and density, are we experiencing a deeply human version of the binding gap? We judge these machines incredibly harshly for dropping their wiring, but perhaps studying exactly how and why artificial intelligence fails to hold the world together might eventually be the key that teaches us how our own fragile, remarkable minds manage to do it at all.
That is an incredible, humbling thought to walk away with. The broken machinery of artificial intelligence holding up a mirror to the fragile, miraculous wiring of human memory. Next time you open a prompt window and use an AI tool, pay attention to the wiring. Look past the fluent prose and the confident tone. Notice if the system keeps the scene but drops the precise attachment. Because you now have a name and a mechanical understanding for exactly what is happening in the high-dimensional math beneath the surface. The binding gap. Thank you so much for joining us on this deep dive. Keep questioning the wiring, stay curious, and we will see you next time.